Hello everybody. In this video, let us see the different ways in which we can construct a B tree. We have already discussed one way in which we can construct a B tree. Anyways, we will recall that here for the sake of understanding the other ways in which we can construct a B tree. So the B tree in which we constructed, a B tree node consisted of m number of keys, where m is the order of the B tree. The order of the B tree is the maximum number of descendants that a node of a B tree can have. So a B tree of order m consisted of m number of keys k1, k2 up to km in the increasing order, that is k1 less than k2 less than k3, so on and so forth, km minus 1 less than km. Okay, and we can have a descendant to the left of key k1 where the subtree will have elements less than or equal to k1. In between k1 and k2 there can be a subtree which will have keys greater than k1 and less than or equal to k2, and here we can have keys which are greater than k minus 1 and less than or equal to km. So this is how we constructed a B tree. So let us construct the B tree for the numbers which are written here and see how this B tree works, and we can see how we can construct a B tree in other alternate ways. So first let us consider the order of the B tree to be 3, means a B tree can have maximum of 3 descendants. So to have 3 descendants in our B tree, the node will have maximum of 3 keys, and minimum it should have m by 2 number of keys, that is 3 by 2, that is 1.5. So we can truncate the fractional part and we can tell that the node can have a minimum of 1 key and a maximum of 3 keys. So now how will we construct a B tree? Since a node can have 3 keys, let us take all the 3 keys together and arrange it in the increasing order 7, 8 and 12. So now the node is full. When we try to insert the next key into the node, a overflow occurs, and overflow is handled by splitting. So now how do we split? So now when 2 is inserted here, the node already overflows, therefore we will divide this node into 2 nodes, one consisting of the keys 2 and 7, other consisting of the keys 8 and 12, and we promote the largest keys present in both the nodes 7 and 12 and form the root node. So now to the left of 7 we will have a descendant, and we will have this descendant in between 7 and 12. So all these keys present in this node are lesser than or equal to 7, and the keys present in this node are greater than 7 and less than or equal to 12. So in this particular fashion we continue constructing our B tree. The next key that we have is 15. So 15 is greater than 7 and it is greater than 12 also. So therefore it has to come in this particular node, and since this happens to be the largest key, that will be promoted to the root node. So now therefore this pointer tells that this subtree consists of keys greater than 7 and less than or equal to 15, and we can notice that this as keys 8, 12 and 15 which are greater than 7 and less than or equal to 15. The next key is 9. So 9, when we try to insert, 9 has to be inserted in between 8 and 12, but we see that the node is already full, therefore this node has to be split into 2 nodes. So what happens is we will have 8 and 9 in one node, 12 and 15 in another node, and here 15 is already there, 7 is already there. The largest key present in this node 9 needs to be promoted to the parent, and that will be inserted in between 7 and 15. Okay, so now this will be the descendant. So now these keys are less than or equal to 7, the keys over here are greater than 7 and less than or equal to 9, the keys here are greater than 9 and less than or equal to 15. So therefore the key B tree property still holds. Next key that we insert is 22. So when we insert 22, 22 is the largest key, 22 will be inserted here, and since it is the largest key, its information will be updated here. So this is how we were constructing the B tree. Okay, so this is one way of constructing the B tree. Now if we can observe this particular B tree very carefully, we can see that all the keys are present in the leaf node, and they may also be present at some higher levels also. Now suppose if this node gets split further, then some keys will be present at the leaf node at this level and at the next higher level also. Okay, say for example if we insert 17. So now if we insert 17 into this particular node, then this node is already full, so it overflows. Therefore what happens, 12 and 15 will be one node, 17 and 22 will be another node, one more key will be promoted, that is 15 will be promoted, and now when 15 gets promoted, this node also overflows. So therefore this will be split into two nodes, 7 and 9, 15 and 22. Sorry, here only we can do it. 15 and 22, and a new parent node is constructed, root node, which consists of 9 and 22. So now the tree looks like this. All the keys in this subtree are less than or equal to 9. All the keys in this subtree are greater than 9 and less than or equal to 22. And the same thing applies at every level. You can see that these keys are less than or equal to 7. Keys greater than 7 and less than or equal to 9. Keys less than or equal to 15. Greater than 15 and less than or equal to 22. So the property holds, and this is a B tree. But one thing what we can see is 7 is appearing in two places over here, and 9 is appearing in all the three levels of the B tree. Same with 22 also. 22 is appearing in all the three levels of the B tree. 15 is appearing in two levels. So therefore, some of the keys of the B tree are appearing at multiple levels in the B tree. This is very much a B tree, but we can also construct, and another thing what we can observe here is the order of the B tree that we considered is 3. So in this particular B tree, a B tree node can have a maximum of 3 descendants because the order is 3. And also there is a relationship between the order of the B tree and the maximum number of keys that can be present in a node. That is, the number of keys present in the node will be equal to the order of the B tree. Any node can accommodate up to 3 keys. Now if you insert one more key, say 25, 25 can come and get accommodated in this particular node because it can have 3 keys and it can have maximum of 3 descendants. So therefore the maximum number of keys in a node and the order of the B tree will be same. So alternately what we can do is we can construct a B tree in which we can eliminate such repetitions, and we can have a key present only once in the B tree, thereby saving space, and therefore the keys need not be repeated at multiple levels. Okay, and also in the B tree that we construct in that particular fashion, the relationship between the maximum number of keys and the maximum number of descendants will not be the same. The maximum number of descendants will be one more than the maximum number of keys that can be present in a node. Meaning, if the order of the B tree is 3, then the maximum number of keys that can be present in a node will be 2, not 3 like how it is happening here. So here if we insert 25, then 25 can exist here. Information about this will be present at both the upper levels. So 3 keys can be present if the order is 3. In the B tree that we are going to discuss next, if the order of the B tree is 3, then the maximum number of keys that can be present is only 2. Okay, how can that happen? Another observation if we can make in this B tree, we have 2 keys and we have only 2 descendants. But we can also have a descendant from the right of 25, which we did not have. Okay, so in the B tree that we are going to discuss next, we will have a descendant to the right of 25 also, that is the largest key present in the node also. And with these changes, we will see how can we construct B tree for the same case of order 3. Okay, so remember one thing, in the B tree that we are going to discuss next, the order of the B tree is 3, but the maximum number of keys that can be present in the node is 1 less than the order, that is 2 number of keys, and also the descendants will be 1 to the left of the leftmost key, in between consecutive keys, and 1 to the right of the rightmost key. The rightmost descendant was not present in the B tree that we discussed just now. Okay, so how are we going to construct this B tree? So once again here we will take 2 keys, 8 and 12, because 2 is the only maximum number of keys that can be present in the node. Next, when we try to insert 7, 7 can't be inserted because this node is already full. So what we will do is we need to split this node. Okay, so how are we going to split? So if we insert 7, 7 comes here, the middle key we are going to promote to the root, not the largest key in each one of the nodes, just like we did in the previous case. Here we will be promoting the middle key to the parent. So therefore what happens, 7 and 12 will be the children and 8 will be promoted as the parent, and we will have 2 descendants, one from the left of 8 and other to the right of 8. So the keys present in this subtree will be less than or equal to 8, and the keys present in this subtree will be greater than 8. So there is no equal to condition. In the previous case we had less than or equal to greater than and less than or equal to, so that equal to condition we can eliminate, and these keys will be less than 8 and these keys will be greater than 8. Next we will see we have to insert 2. So 2 is less than 8. We come here, we insert 2. So 2 number of keys can be present in a node, therefore that exists. 15. So 15, when we insert, 15 is greater than 8, it is greater than 12, therefore 15 gets inserted here. We need not promote like we did earlier, because the keys present over here must be greater than 8, they are greater than 8, these are less than 8. So therefore there is no problem. Next key that we need to insert is 9. So 9 is greater than 8, and among these two keys it is less than 12. So 9 has to come here. So now since this node overflows, the node can't exist. It needs to be split. And which is the middle key? The middle key is 12. So 12 will be promoted to the parent, and there will be a descendant from in between 8 and 12, and one descendant from right of 12. So now we can see all these keys are greater than 8, these keys are greater than 8 and less than 12, and these keys are greater than 12. So in this particular fashion we can continue constructing the B tree. The next node that we insert is 22. So when we insert 22, this is where it gets inserted and there is no need for any promotions. Okay, so the same thing can be applied even if this node splits and a new root is formed. Say suppose we insert 25, let us assume, just like in the previous case, here also we'll assume 25 is inserted. 25 can be inserted here, but now this node can't exist because it overflows. Therefore we promote the middle key, 22. Okay, so when 22 is promoted here, we can see this node also overflows. It can hold only 2 keys. This is the third key that we are inserting. Therefore this also will be split into 2, and the middle key will be promoted to the parent. This will become the left descendant, this will become the right descendant. So now this is the B tree that we have. So all these keys are less than or equal to 12, all these keys are greater than or equal to 12, and this applies at every level. Here the keys are less than 8, here the keys are greater than 8, less than 22, greater than 22, and this is still a B tree with no repetition of the keys. No keys are repeated anywhere, and we can see that there is a right descendant also from the rightmost key, which was not there in the previous B tree. Okay, so this depends upon the application, how we want to construct the B tree. Okay, so these are the two ways of constructing B tree when we have integer numbers. For the sake of simplicity, we consider integer numbers and try to construct the B tree. But in real-time applications, sometimes the keys may not be integer numbers and it may be strings also. Say for example, the keys are names using which we need to construct the B tree. So if we have strings, how can we construct the B tree? So one thing is we can consider the whole string as the key and construct a B tree the same way that we discussed just now. Say suppose you have a key ABCD, okay, and another key PQR, then we can just keep inserting these keys into the node of a B tree depending upon the order, and we can keep splitting and doing various operations of the B tree. Okay, then another key is inserted, say MN, then MN gets inserted in between. Okay, and now if we consider order is 3, and if we are following the second approach for constructing the B tree, then this overflows, then MN goes to the root, this will become the left child and this will become the right child. So this is how we can construct a B tree when we have strings. But one thing, if we can observe, see these keys may be of variable length and they may occupy more space in the block in which we are storing the keys, means each node of the B tree, thereby allowing fewer number of keys to be accommodated in each nodes of the B tree. Okay, the purpose of the B tree is to assist us in searching whether we should move towards the right or towards the left to find the actual data record. This will finally give the reference of the data record which is present in the hard disk. Okay, so therefore it may not be necessary for us to have the whole strings as keys. Okay, we can try to minimize the key length and we can construct a B tree which can still assist us in searching the data records. How can we do that? Okay, for that there can be many approaches. One simple approach what we can consider is to construct what is called as a prefix. Okay, we can construct a prefix from the keys that are available here, and using those prefixes we can construct a B tree so that the number of size of each one of the keys in the nodes will be smaller and more keys can be accommodated in any node of the B tree. How can we do that? Okay, so now let us take the same example and see how we can construct a prefix B tree. Okay, so now when we want to construct a B tree, okay, so let us assume there are some number of keys. Let us not worry about the order of the B tree, okay, because we need to see how we can construct prefix B trees. Okay, so there are some number of keys, m number of keys that are present in this particular node, and the node has become full at this point of time, let us assume, when some key was inserted. Okay, and now the insertion of next key into this particular node causes an overflow. When an overflow occurs, this node needs to be split. Okay, when it splits, it becomes two halves. Okay, and we will construct a prefix which will assist us in searching by considering the last key of the first block and the first key of the second block. Okay, so let us assume the last key of this node after splitting is say KLM. Okay, and in the second node let us assume that we have a record PQ and it ends at first. Let us take A, B, C, D, X, Y, Z are the first and the last keys. When we split, let us assume here the last key is K, L, M, and here the first key is PQ. Okay, PQ and X, Y, Z. PQ is the first key, X, Y, Z is the last key. So now we will construct a prefix by taking these two keys. How do we construct the prefix? So now to construct the prefix, what we do is we match the corresponding characters of the last key of the first block with the first key of the next block. As many characters match, those many characters will appear in the prefix key that appears in the B tree, plus one extra character which we can take from either of these keys. How does that work? So let me explain with this example. So now here the first character is K, the first character here is P. Okay, when we compare, we see that these two characters don't match. So since they don't match, P itself is sufficient for us to make a decision as to whether we have to go to the left or we need to go to the right in order to find the key that we are looking for. So whenever I am searching for some key, say I am searching for some key CD. So CD is less than P, C is less than P. Therefore, it tells me that I need to proceed to the left subtree if I need to find the record with key CD. So I will come to this particular block A, B, C, D, K, L, M. If at all CD was present, CD must be present. In between this, it is not present, so search is unsuccessful. Okay, or I need to search K, L, M itself, let me assume. So in that case, what I will do, I will come here K and P. Okay, K is less than P. I will come to this block. In the block sequentially, I keep comparing and finally I find that K, L, M is present here. Okay, if I am searching for XYZ, X is greater than P, so that suggests me to go to the right block, and here if I keep comparing sequentially, finally I will find XYZ somewhere in the node. So in this particular fashion I can proceed my search. So this is one example wherein the very first characters don't match. Sometimes some number of characters may match and a mismatch can occur somewhere in the middle. Okay. So let us consider one such example. Okay, so now let us assume keys are getting inserted into this particular block, and at some point of time this particular block overflows and it splits. Okay, so now when it splits, let us assume the last key of this particular block is S, T, and the first record in this block is U, V. Okay, STU, and here it is STUVW, let us assume. Okay, X, Y, Z. So now when we form the prefix, here we have STU and here we have STUVW. Okay, so we compare S and S, both of them match, so therefore the prefix will include S. Then T, both of them match, so T will be included in the prefix. U and U will be included in the prefix. Now this key got exhausted, so therefore we will take the next key, that is V, and STUV will become the prefix using which we can differentiate between this block and this block, and STUV will be included in the root node. Okay, so now this will become subtree in between P and STUV. So now all the keys whose value is less than P will be present here, greater than P and greater than or equal to P. Okay, so here less than or equal to P, and this one will be greater than or equal to P and less than STUV. Okay, so this one will be greater than or equal to STUV, okay, and less than XYZ. Okay, now this is still a B tree because it assists us in searching the keys, but we are not using the complete keys, the entire length of the key in the B tree, in the search tree. We are using only a portion of it. Okay. The same way, the root node may also split, and that may have to be promoted to the new root may have to be formed, and one of the keys from here may have to be promoted to the root. So that we will do in a similar fashion. Okay. So sometimes it may so happen that the second key may become the depending upon the last key and the first key of the consecutive blocks, an entire key of the second block may become the key prefix key in the root, because say suppose the keys are something like this. So now STUV, if suppose this key itself was just STUV and this was STU, so now what happens, S and S will be compared, S will appear in the prefix, T and T will be compared T, U and U will be compared U. Okay, and now this key got exhausted, but there is one more character and that is the last character, so STUV. So STUV will be included in the root, and once again the search tree will look in the similar fashion. Okay, so same way we can continue constructing the B tree. So now suppose this node gets, let us assume this node gets split, A, B, C, D. The last key over here is CD or just C, one character, and the first key over here is E, let us assume. Okay, so now when we try to form a prefix, we see that the first character themselves don't match, and therefore E can be promoted as the key to the parent. And since if we assume that this node also splits for the sake of understanding, then P will become the root. To the left of P we will have E, and this will be to the left of E, and this will be to the right of E. So the keys are less than or equal to E, greater than or equal to E, okay, and here less than or equal to STUV, greater than or equal to STUV, and this subtree will have all the keys less than or equal to P, and this subtree will have keys greater than or equal to P. So by doing this, what we are trying to do is we are making sure that we can accommodate more number of keys in each one of the nodes, because we are forming simple prefixes. We are not having an entire key present at all the levels in the node. Okay, so these are some of the ways in which we can construct B trees. Thank you.